Did you know that in the vast emptiness of space, there are places where stars scream silently, black holes hum melodies we can't hear, and entire galaxies spin like dancers in the cosmic dark? The universe is more bizarre, more awe-inspiring than anything our imaginations could conjure, and today we're diving headfirst into its deepest mysteries. Picture this: you're floating in the infinite void, surrounded by wonders so strange they defy logic, so beautiful they steal your breath. That's the reality of space, a realm where the rules we know don't always apply, and every discovery feels like uncovering a secret the cosmos has been keeping for billions of years. Think about the last time you looked up at the night sky and felt that tug of wonder. Maybe you counted stars, traced constellations, or marveled at the sheer scale of it all. But here's the thing: what we see is just the tiniest glimpse of the universe's true grandeur. Beyond those twinkling lights lie phenomena that bend the laws of physics, celestial bodies older than time itself, and mysteries that even the sharpest scientific minds are still scrambling to solve. From planets where it rains glass sideways to stars so massive they could swallow our sun without a burp, space is a never-ending source of wait that can't be real, can it? Moments, and that's exactly what we're exploring today. 30 of the most mind-blowing, hair-raising, downright unbelievable facts about space that will leave you questioning everything you thought you knew. These aren't your textbook trivia tidbits, no. These are the kind of revelations that make you pause mid-scroll, stare into the distance, and whisper, "How is that even possible?" So buckle up, because we're about to take a journey through the cosmos that'll twist your sense of reality, stretch your imagination, and maybe, just maybe, make you see that glittering night sky in a whole new light. Ready to have your mind blown? Let's go. Right now, as you're watching this, the moon is inching away from us slowly, silently, at the rate your fingernails grow. Every year, our cosmic companion drifts 3.8 centimeters farther into the black. It might not sound like much, but over millions of years, that tiny distance adds up to a dramatic reshuffling of Earth's rhythms. Imagine a dancer stepping back, stretching the tether between partners. That's the moon pulling away from Earth's gravitational embrace. This cosmic slow-motion escape began 4.5 billion years ago, when a Mars-sized object smashed into our young planet, spraying debris that eventually coalesced into the moon. From day one, it's been retreating, its orbit widening like a spiral unwinding across the ages. Here's where it gets wild. As the moon distances itself, Earth's rotation is actually slowing down. Think of a figure skater extending their arms to slow a spin. Our planet's tides act like invisible arms dragging against the oceans. Those daily tugs of war between Earth's rotation and the moon's gravity transfer energy, pushing the moon outward while putting the brakes on our day. 500 million years ago, a day on Earth lasted just 21 hours. Fast forward another few 100 million years, and future sunrises will stretch longer than we can fathom: 25, maybe even 30-hour days, with tides so feeble they barely lap at the shore. But don't panic just yet. The moon won't vanish entirely, at least not before the sun swells into a red giant and engulfs both of us. Long before that, though, the sky will change in subtle, surreal ways. A more distant moon means no more total solar eclipses. It'll appear too small to fully cover the sun, and those iconic footprints left by Apollo astronauts. They'll still be there, undisturbed in the silent retreat, a fossilized hello from a time when the moon hung just a little closer in our sky. So next time you gaze up at it, remember, you're witnessing a cosmic farewell in slow motion, a celestial dance with steps measured in centimeters and lifetimes measured in millennia. While Earth and most planets spin counter-clockwise like graceful tops, Venus defiantly dances to its own rhythm, spinning clockwise in what astronomers call a retrograde rotation. Picture this: if you could stand on Venus's scorching surface, which you absolutely couldn't, but we'll get to that. the sun would rise in the west and set in the east, moving backward across a sky choked with sulfuric acid clouds. This isn't just a quirk, it's a full-blown cosmic rebellion against the usual order of our solar system. What makes Venus's backward spin even stranger? It's not alone in its defiance. Uranus also rolls on its side like a tipped-over barrel, but Venus takes the prize for sheer audacity. While most planets tilt modestly on their axes, Venus is nearly upside down, rotating at a sluggish pace that makes its day longer than its year. That's right, it takes 243 Earth days for Venus to complete one rotation, but only 225 Earth days to orbit the Sun. Time there isn't just slow, it's practically unraveling in reverse. So how did Venus end up like this? Scientists have two leading theories, each as dramatic as the planet itself. The first suggests a cataclysmic collision, a planetary-scale smash-up early in the solar system's history that literally knocked Venus spinning the wrong way. The second theory blames the planet's thick, suffocating atmosphere, which may have generated tidal forces strong enough to gradually reverse its rotation over billions of years. Imagine a ball submerged in syrup. The drag eventually alters its spin. Venus's atmosphere is 90 times heavier than Earth's, with clouds that whip around the planet at hurricane speeds, so this slow-motion cosmic tug-of-war isn't just plausible, it's probable. And speaking of that atmosphere, Venus doesn't just spin backward, it cooks under conditions straight out of a nightmare. Surface temperatures soar to 860 degrees Fahrenheit, hot enough to melt lead. The crushing air pressure feels like diving a mile underwater, and those beautiful clouds, they're made of sulfuric acid, raining droplets that evaporate before hitting the ground. It's a world where the very sky is corrosive, the ground glows faintly from heat, and the only visitors, Soviet landers in the 1970s, lasted mere minutes before succumbing to the inferno. Yet for all its hostility, Venus holds clues to planetary evolution. Its retrograde spin and hellish climate might be the result of a runaway greenhouse effect, a warning written across the cosmos of what happens when a planet's balance tips too far. As we search for life beyond Earth, Venus reminds us that even in the familiarity of our solar system, the universe still has twists we're only beginning to understand. So next time you see the evening star gleaming after sunset, remember, that serene light hides a world spinning defiantly, stubbornly, wonderfully out of step with everything around it. Here's a cosmic riddle for you. What if every birthday passed in the blink of an eye, but waiting for sunset felt like an eternity? Welcome to Mercury, where time itself seems broken, a planet where a single day lasts longer than an entire trip around the sun. While Earth pirouettes through its year with predictable grace, Mercury stumbles through a dizzying cosmic waltz. It spins so out of sync with its orbit that sunrise becomes a rare celestial event. Let's put this in perspective. On Earth, we take our 24-hour day and 365-day year for granted. But Mercury's tiny frame, just slightly larger than our moon, is locked in a gravitational tug-of-war with the sun so intense it's reshaped time itself. One orbit around the sun, a brisk 88 Earth days, but a full rotation on its axis, a sluggish 59 Earth days. That mismatch creates a bizarre phenomenon. From sunrise to sunrise on Mercury, you'd wait a staggering 176 Earth days, 2 full Mercury years. Imagine celebrating 2 New Year's Eve parties before your first cup of morning coffee. Why such chaos? Blame the sun's overwhelming grip. Mercury orbits so close to our star that tidal forces have slowed its rotation to a crawl, like a dancer struggling to spin while anchored by an invisible rope. Scientists call this spin-orbit resonance, a fancy term for how Mercury rotates 3 times for every 2 trips around the sun. The math defies intuition. 3 spins divided by 2 orbits equals days that outlast years. The consequences are surreal. Near Mercury's hot poles, points facing the sun at closest approach temperatures rocket to 800 degrees Fahrenheit, hot enough to liquefy zinc. But its slow rotation means other regions spend Earth months in frigid darkness, plunging to negative 290 degrees. And here's the kicker. If you stood in a magically heat-proof suit at certain points on Mercury's surface, you'd witness the sun perform a cosmic U-turn. It would rise, pause, backtrack briefly across the sky, then resume its journey, all thanks to Mercury's lopsided orbit briefly outpacing its spin. This tiny world teaches us how fragile time can be when gravity pulls the strings. While Earth's steady rhythms lull us into predictability, Mercury screams that the universe has no obligation to make sense by our standards. Its twisted calendar is a reminder. Out there, the rules are written by forces so vast they can stretch a sunrise across seasons. Somewhere in the constellation Cancer, 40 light-years from Earth, a planet shimmers with impossible luxury, a world where mountains might gleam like cut jewels and rivers could flow with molten diamond. Welcome to 55 Cancri E, an exoplanet so rich in carbon that scientists believe much of it has crystallized into one of the universe's most fantastical substances. Forget gold or platinum. This is a planet where the very ground beneath your feet, if you could stand on its 2,000-degree surface, might be worth quadrillions. Here's how such a jewel box world could exist. Most rocky planets like Earth form from silicon and oxygen ingredients that make humble sand and stone. But 55 Cancri E orbits a star with unusually high carbon levels, meaning the planet likely formed from carbon-rich material. Under extreme heat and pressure, think temperatures rivaling lava, and pressures 1,000,000 times greater than Earth's atmosphere, carbon atoms rearrange into crystalline lattices, diamond. Picture the entire planet as a cosmic pressure cooker, where carbon gets squeezed and baked over billions of years until it transforms into something glittering and alien. But don't pack your mining gear just yet. 55 Cancri E isn't a Tiffany's display case floating in space. For one, its surface is probably a searing wasteland of graphite and diamond hybrids, with conditions so harsh they defy even sci-fi imagining. The planet is tidally locked, meaning one side forever faces its star, broiling under perpetual daylight, while the other languishes in eternal darkness. That sunlit side, a 2,000-degree nightmare where diamonds might not even stay solid, they could melt into carbon oceans, churning under a sky thick with vaporized rock. And here's the twist, 55 Cancri E might not be alone. Astronomers speculate that carbon-rich planets could be common around stars with similar compositions, meaning our galaxy could be littered with these diamond-encrusted oddities. Some might even harbor layers of diamond hundreds of miles thick, sandwiched between molten metal cores and atmospheres of carbon monoxide. It's a reminder that the universe's creativity outshines our wildest fantasies, turning the stuff of engagement rings into entire worlds. Yet for all its allure, 55 Cancri E is less a treasure trove and more a laboratory for extremes. Studying it challenges our assumptions about planet formation, showing how a slight change in stellar ingredients can birth something utterly unrecognizable. So while we'll never walk its diamond-studded plains, this glittering enigma teaches us a valuable lesson. Out there, in the dark, the cosmos is always rewriting the rules of what's possible. For over 300 years, Jupiter's great red spot has swirled like a furious eye in the gas giant's atmosphere, a storm so vast it could swallow Earth whole. But this legendary tempest, once the undisputed king of planetary weather systems, is showing signs of weakness. Recent observations reveal it's shrinking, its once mighty winds slowly losing their grip on the chaos they've commanded since astronomers first spotted it in the 1600s. Picture a hurricane that outlasts civilizations. The Great Red Spot isn't just a storm, it's a planetary-scale maelstrom, with winds screaming at 400 miles per hour and a crimson-tinged vortex deeper than Earth's oceans. Its color, likely caused by sunlight breaking apart chemicals like ammonia and acetylene, shifts from brick red to pale salmon, as if the storm itself is breathing. For centuries, it's been Jupiter's most recognizable feature, a constant in the ever-changing tapestry of the solar system's largest planet. Yet time-lapse footage from the Hubble Space Telescope tells a different story. Since the 1800s, astronomers have watched the storm's girth contract. Once wide enough to fit 3 Earths side by side, it's now barely larger than our planet, and it's not just shrinking, it's changing shape. What was once a proud oval is becoming more circular, like a weary boxer dropping their guard. Some years, the spot even flakes apart at the edges, shedding smaller storms like splinters from a spinning top. What's strangest isn't just the shrinking, it's that we still don't fully understand why. Some scientists argue Jupiter's jet streams, those ribbons of wind that race around the planet, are slowly choking the storm. Others suggest internal turbulence is sapping its energy, or that mysterious processes deep beneath the clouds are altering the spot's fuel supply. Unlike Earth's hurricanes, which fade when they hit land or cool waters, Jupiter's great red spot has no surface to disrupt it. It's a self-sustaining monster feeding on the planet's own heat, and its decline defies easy explanation. Here's the twist: the great red spot might not be dying so much as transforming. Some researchers believe it could stabilize at a smaller size, persisting for centuries more. Or it might vanish entirely, leaving Jupiter's face unrecognizable to future generations. Either way, we're witnessing a cosmic rarity, the slow-motion unraveling of a storm older than the United States, a reminder that even the mightiest phenomena in our solar system are fleeting when measured against the vast scales of space and time. So the next time you see Jupiter gleaming in the night sky, remember, that tiny pinkish dot in its southern hemisphere is a living fossil, a storm that's raged since telescopes were a new invention. And whether it's in its final act or just beginning a new chapter, its story is written in winds we're only starting to decode. Imagine a star so dense that a single teaspoon of its material weighs 1 billion tons, a cosmic wrecking ball spinning hundreds of times per second, flinging beams of radiation across the galaxy like a lighthouse gone mad. This isn't science fiction, it's the reality of neutron stars, the collapsed cores of massive stars that went supernova but refused to fade quietly into the dark. These stellar zombies are born from explosions so violent they squeeze protons and electrons together, crushing atoms into a sea of pure neutrons. The result: a city-sized orb with the mass of our sun, spinning faster than a kitchen blender and armed with magnetic fields strong enough to erase your credit card from halfway across the solar system. But neutron stars have a party trick that makes them truly unforgettable. Some of them pulse. When a neutron star's magnetic poles don't align with its spin axis, it becomes a pulsar, a celestial strobe light shooting beams of radio waves, X-rays, or gamma rays into space with metronomic precision. Picture a rotating spotlight on a cosmic scale. As the star spins, those beams sweep past Earth like clockwork, creating pulses so regular they rival atomic clocks. The first pulsar discovered, whimsically nicknamed LGM-1 for Little Green Men, had astronomers briefly convinced they'd stumbled upon an alien distress signal until they realized nature itself was the mastermind behind such perfect timing. The speeds these stars achieve defy comprehension. The fastest known pulsar, PSRJ 1748-2446 AD, whirls at 716 revolutions per second, so rapid its surface moves at nearly a quarter the speed of light. At that rate, a single day on Earth would feel like 50,000 years to someone clinging to its surface, if they weren't immediately vaporized by gravity 100 billion times stronger than ours. And the energy they emit, the Crab pulsar, born from a supernova observed in 1054, unleashes enough power in its beams to light up entire planetary atmospheres from light years away. Yet pulsars aren't just cosmic curiosities, they're tools. Astronomers use their steady ticks to test Einstein's theory of relativity, map the galaxy's magnetic web, and even navigate spacecraft. The Voyager probes carry pulsar maps as interstellar GPS, with star positions coded in pulse frequencies, a message in a bottle for any civilization that might find them. And when two neutron stars collide, the resulting gravitational waves ripple spacetime itself, scattering gold and platinum across the cosmos like cosmic glitter. So the next time you gaze at the night sky, remember, hidden in the static between the stars are these unbelievable spin tops, their rhythmic beats whispering secrets about the universe's most extreme physics. They're dead stars that refuse to die quietly, lighthouses not for sailors, but for the entire galaxy. The sun may look like a golden coin in our sky, but that's just cosmic sleight of hand, an illusion created by the sheer distance between us and a furnace so massive it defies human comprehension. At its core, where temperatures reach a blistering 27 million degrees Fahrenheit, you could cram 1.3 million Earths side by side and still have room to spare. That's not just big, that's a volume so vast it would take our planet, lined up like marbles, stretching from here to well beyond the moon. What makes this even wilder? The core, where all the magic happens, only accounts for about 1% of the sun's total volume. It's the ultimate case of tiny but mighty, a space no larger than Jupiter's orbit around the sun, yet responsible for generating nearly all the energy that fuels our solar system. Here, under pressures 250 billion times stronger than Earth's atmosphere, hydrogen atoms slam together in a relentless nuclear dance called fusion. Every second, 600 million tons of hydrogen fuse into helium, converting enough mass into energy to power civilization for 500,000 years. But here's what really bends the mind. The light produced in those reactions takes a bizarrely long journey to reach us. Photons born in the core don't zip straight out. Instead, they bounce around like pinballs in the sun's dense interior, colliding with atoms for up to 100,000 years before finally breaking free. By the time that light reaches the surface and races toward Earth in just 8 minutes, it's already ancient, a cosmic relic from an era when humans were just beginning to walk upright. And yet, for all its ferocity, the sun is a study in balance. The outward push of fusion fights a perpetual tug of war with gravity's inward crush, creating a stable furnace that's burned for 4.6 billion years without exploding or fizzling out. It's a reminder that scale in the universe isn't just about size. It's about forces dancing on a knife's edge, where a star's life depends on the precision of physics we're still struggling to replicate here on Earth. So the next time you feel the sun's warmth, remember, you're basking in the afterglow of a reactor so efficient, so unimaginably vast that its heart could swallow our world 1,000,000 times over and still have space to spare. In the endless expanse of the universe, there's one thing you'd never hear: absolutely nothing. Space isn't just quiet, it's utterly, profoundly silent, a vacuum where sound simply can't exist. Forget the roaring engines of sci-fi starships or the explosive crashes of asteroids. Those are Hollywood fantasies. Reality is far eerier. No matter how colossal the cosmic event, from supernovas obliterating stars to galaxies colliding in slow motion, it all happens in perfect, unsettling silence. Why? Sound needs something to travel through: air, water, even solid objects, vibrating molecules like a game of telephone. But space is nearly a perfect vacuum, with atoms so sparse they might as well be lonely travelers in an empty desert. A single cubic centimeter of Earth's air holds trillions of molecules. The same space between stars might hold just a handful. So when a star explodes or black holes merge, the vibrations have nothing to push against, no medium to carry their energy. The universe watches these cataclysms play out like a muted television screen, all spectacle, no soundtrack. This silence creates surreal scenarios. If you were floating near two colliding galaxies and somehow survived the radiation, you'd witness billions of stars rearranging in perfect stillness. An astronaut scream outside their spacesuit, gone the moment it leaves their lungs, swallowed by the void. Even the sun, that roiling ball of plasma, doesn't actually roar. Its violent eruptions ripple through magnetic fields, but those waves can't reach our ears. The only way we hear space is by translating other signals, like radio waves or ultraviolet light, into sound, a human-made illusion to connect with a universe that communicates in wavelengths beyond our natural senses. Yet this silence isn't empty. It's a canvas for other cosmic sounds. Pulsars emit rhythmic radio pulses we can convert into chirps. The leftover echo of the Big Bang hums in microwave frequencies. And in 2015, scientists even detected gravitational waves, ripples in spacetime from black holes colliding, which, if scaled up, would produce a chirp barely audible to human ears. These aren't true sounds, but they reveal a deeper truth. Space speaks in vibrations we're only learning to decode. So while the movies fill the cosmos with laser blasts and engine rumbles, the real universe unfolds in a silence so vast it's almost haunting. It's a reminder of how alien space truly is, a realm where even the most violent events whisper their secrets to those patient enough to listen, without expecting to hear a thing. 12 billion light-years away, floating in the cosmic deep, there's a cloud so massive it defies logic, a single concentration of water vapor holding 140 trillion times all the water in Earth's oceans. To put that incomprehensible number in perspective, if you could gather every drop from our planet's rivers, lakes, ice caps, and even the moisture in the air, you'd need to multiply it by 140 trillion just to match this celestial reservoir. It's not just a pool in space, it's an ocean larger than our solar system, wrapped around a feeding supermassive black hole known as a quasar. Quasars are the universe's ultimate powerhouses, black holes so voracious they outshine entire galaxies as they devour matter. The water cloud, discovered in 2011, orbits one such monster named APM 08279 plus 5255. Scientists caught its signature using the Z-spec instrument at the Caltech Submillimeter Observatory, detecting the faint microwave whispers of water molecules stretched across hundreds of light years. The environment is anything but serene. The quasar's radiation tears through the cloud, churning it into a maelstrom of vapor and ice, with temperatures hitting -63 degrees Fahrenheit and densities 5,000 times thinner than our atmosphere. What's astonishing isn't just the water's scale, it's what it tells us about the early universe. This cloud existed when the cosmos was barely 1.6 billion years old, proving water was abundant even during the universe's chaotic infancy. Astronomers suspect such reservoirs are cosmic factories, their moisture eventually coalescing into icy comets or even the oceans of nascent planets. The water molecules likely formed on interstellar dust grains, where oxygen atoms bonded with hydrogen in the cold voids between stars, a process still happening today in nebulae across the galaxy. Yet this cloud's fate is as dramatic as its origin. The quasar's gravity will eventually warp and compress it, some water freezing into comets flung across the galaxy, some vaporized into plasma, and perhaps, just perhaps, a fraction someday irrigating the soils of a world not yet born. It's a reminder that the ingredients for life aren't just Earth's treasures, they're scattered across the cosmos, waiting in the dark for the right conditions to awaken. So while we marvel at Earth's blue oceans, remember, we're just a drop in a universe that's drenched. Ever stepped on a scale and wished the number were lower? Well, here's some cosmic relief. Your weight isn't as fixed as you think. In fact, it's a sliding scale depending on where you stand in the solar system, dictated by the relentless tug of gravity. That force holding you to Earth right now, it's not universal. On Mars, you'd bounce like an astronaut on a trampoline, while Jupiter's crushing grip would make you feel like you've been stuffed under a mountain. Let's break it down. Gravity depends on two things: a planet's mass and your distance from its core. Earth, our familiar benchmark, pulls you down with a force we call 1 g, about 9.8 meters per second squared. But venture to Mars with just a tenth of Earth's mass, and suddenly you're 62% lighter. A 150-pound person would feel like a mere 57 pounds, leaping over rocks with the ease of a kangaroo. Now flip the script and visit Jupiter. The gas giant's immense mass, 2.5 times that of all other planets combined, creates gravity 2.5 times stronger than Earth. That same 150-pound human, now they're buckling under 375 pounds of imaginary weight, their bones groaning under pressure fit to crush submarines. Even Jupiter's moons aren't safe. Io's volcanic fields and Europa's icy crust are stretched and squeezed by the planet's monstrous pull. But here's where it gets fun. Imagine stepping onto Pluto, where gravity is just 6% of Earth's. You'd weigh less than a house cat here, launching yourself dozens of feet with a single stride. Or picture Mercury, small but dense, with gravity 38% of Earth's. You'd feel eerily light, yet not quite floating, like you're stuck in permanent moonwalk mode. And let's not forget the Sun, the ultimate heavyweight. Its gravity accounts for 99.8% of the solar system's total mass. Stand on its surface if you could survive the 15 million degree heat, and you'd weigh 28 times more than on Earth. Every muscle would scream under the load, a cruel reminder of the star's dominance over everything orbiting it. Ready for a game? Pause and guess. What would you weigh on Saturn, where the planet's density is so low you'd actually weigh slightly less than on Earth despite its size? Or on Venus, a near twin in mass to our world, but with an atmosphere thick enough to crush spacecraft in minutes? The answers might surprise you. Gravity's quirks make the solar system a cosmic funhouse of shifting scales. This isn't just trivia, it's a lesson in how wildly planetary conditions vary. Gravity shapes atmospheres, determines whether a world can hold liquids, and even influences how tall mountains can grow before collapsing under their own weight. So next time you complain about your weight, remember, in the grand cosmic gym, the universe offers plenty of ways to tip the scales. Deep in laboratories right here on Earth, scientists have crafted something the universe itself could never produce naturally, a state of matter so cold it defies intuition. This is the Bose-Einstein condensate, a bizarre substance where atoms lose their individuality and behave as a single quantum wave, creeping just billionths of a degree above absolute zero. That's negative 459.67 degrees Fahrenheit colder than the void between galaxies, colder than the afterglow of the Big Bang, colder than even the Boomerang Nebula, once thought to be the universe's natural icebox. How is this possible? In the mid-1990s, physicists used lasers and magnetic traps to slow atoms to near motionless states, stripping them of energy until they merged into a quantum soup. Picture a dance floor where everyone moves in perfect unison, no twirls, no shuffles, just a single, eerie synchronicity. At these temperatures, atoms lose their chaotic nature and enter a state where quantum effects, usually invisible to our eyes, become macroscopic. Droplets of condensate can climb walls, pass through barriers like ghosts, or even stop light in its tracks, storing information in their frozen embrace. Now here's the cosmic irony. While these lab-made cold spots hold records, space itself is far from chilly. The cosmic microwave background, the faint glow left over from the Big Bang, bathes the universe in a warmth of 2.7 Kelvin, or negative 454.7 degrees Fahrenheit. That's warmer than our artificial deep freezes. Even Pluto's icy plains or the shadowed craters of Mercury can't compete with the chill of a Bose-Einstein condensate. Yet the coldest natural place we found, the Boomerang Nebula, where gas expanding at 300,000 miles per hour drops temperatures to 1 Kelvin, just a whisper above absolute zero. But even that can't touch the ultra-cold realms we've engineered. It's a reminder that nature's extremes often pale next to human ingenuity, that inside unassuming labs we've outdone the cosmos at its own game. So next time you shiver on a winter night, remember, The deepest cold isn't in the void of space or the heart of a nebula. It's right here on Earth, in machines where atoms learn to move as one, showing us the universe's hidden rules in ways the stars themselves never could. Imagine holding a teaspoon of sugar, just a few harmless grains. Now picture that same spoon filled with material so dense, it outweighs every car, every skyscraper, every mountain on Earth combined. That's the reality of neutron star matter, where the carcass of a dead star gets compressed into a nuclear nightmare so extreme it defies every law of density we know. To grasp this, let's stack it against Earth's heaviest substances. A teaspoon of gold, about 400 grams. A teaspoon of lead, not even 700. But a neutron star's crust, if you could somehow scoop it, would weigh in at a staggering 1 billion tons. That's like stuffing Mount Everest into a coffee mug and still having room for 3 more. This isn't just heavy, it's matter folded in on itself, atoms crushed until electrons and protons merge into a sea of pure neutrons with no empty space between them. How does a star become this absurdly dense? It starts with a violent death, when a massive star, at least 8 times heftier than our Sun, runs out of fuel. It doesn't fade gently. Its core collapses in seconds, triggering a supernova explosion bright enough to outshine galaxies. What's left isn't a star anymore, but a city-sized orb packing all that original mass into a sphere no wider than Manhattan. The gravity is so intense that if you dropped a marshmallow onto its surface, it would hit with the energy of a nuclear bomb. But here's the real kicker: neutron stars aren't just dense, they're cosmic shapeshifters. Under that crushing gravity, matter behaves in ways impossible on Earth. Protons and electrons get squeezed together until they form neutrons, hence the name. Some theories suggest the cores might harbor even weirder states, strange matter made of quarks freed from their usual confines, or superfluids that flow without friction. It's a laboratory for physics we can't replicate, where the rules get rewritten by sheer gravitational force. And yet, for all their ferocity, neutron stars have a delicate side. Their crusts are crystalline, possibly the strongest material in the universe, capable of forming mountains, barely millimeters tall before gravity flattens them. Even their spin is precarious. Some rotate hundreds of times per second, flinging beams of radiation like lighthouses, while others slow to a crawl over millennia. They're the universe's ultimate paradox, monstrous yet precise, destructive yet beautiful. So the next time you stir sugar into your coffee, think about that teaspoon's cosmic counterpart, a relic of stellar catastrophe where a single spoonful holds the weight of worlds. It's a reminder that out there, matter doesn't play by our rules. Let that sink in for a moment. Every grain of sand you've ever let slip through your fingers at the beach, every dune you've climbed, every hourglass you've flipped represents just a fraction of the stars shimmering in the cosmos. Scientists estimate Earth's beaches hold around 7.5 quintillion grains of sand. That's a 7 followed by 18 zeros, a number so vast it dwarfs the human brain's ability to comprehend. Yet the universe laughs at such earthly totals. Our Milky Way alone houses roughly 100 billion stars, and astronomers calculate there are at least 2 trillion galaxies in the observable universe. Do the math, and you're staring at a figure so colossal it rewires your sense of scale. 10,000 stars for every single grain of sand on our planet. This isn't just about big numbers, it's about redefining what countless really means. Picture standing on a beach stretching to the horizon, scooping up a handful of sand. Those tiny fragments in your palm, they'd correspond to a celestial metropolis of stars scattered across light years, each potentially hosting its own planets, moons, and mysteries. Now imagine repeating that across every beach on Earth: California's shores, the Sahara's dunes, remote atolls barely touched by waves. Even then, you'd barely scratch the surface of the cosmos's stellar census. And here's the twist: those estimates are conservative. The actual number of stars could be far higher. dwarf galaxies, rogue stars drifting between galaxies, and faint red dwarfs invisible to our telescopes pad the real total. Even the sand comparison has caveats. New research suggests some deserts and ocean floors might hold untold reserves, pushing Earth's grain count higher. But it doesn't matter. However you tally it, the universe wins, spinning out stars with a profligacy that humbles our attempts to quantify it. What does this mean for our place in the cosmos? It's not just that we're small, it's that space operates on a scale where small loses meaning. Those stars aren't just points of light, they're nuclear furnaces, some with planets where chemistry might be stitching together who knows what. The sand you shake from your shoe, it's a reminder that Earth, for all its beauty, is a speck in a gallery where the art outnumbers the walls. So next time you're seaside, let the absurdity wash over you. Every grain underfoot is a cosmic counter, whispering that out there, the lights will never ever run out. The Milky Way has a dirty little secret. It smells like a cosmic distillery. Floating in the vast clouds of gas between stars, astronomers have detected ethyl formate, the very same molecule that gives raspberries their sweet tang and rum its rich, fruity aroma. That's right, our galaxy is practically marinating in the scent of intergalactic mojitos. This isn't just poetic license. In 2009, scientists using the ARAM telescope in Spain pinpointed this quirky compound in Sagittarius B2, a giant molecular cloud near the Milky Way's center. Alongside ethyl formate, they found other organic molecules like vinegar acetic acid and the sharp bite of rotten eggs hydrogen sulfide, mixing into what one researcher joked was the smell of a bad morning after. The discovery wasn't just a whimsical headline, it revealed how complex chemistry thrives even in the freezing emptiness of space, where temperatures hover near absolute zero and atoms barely bump into each other. But how does a galaxy smell at all? In space, no one's nose is there to sniff, but these volatile compounds leave fingerprints in the light they emit. When starlight passes through clouds of gas, molecules absorb specific wavelengths, creating dark lines in the spectrum like a barcode. Decode those lines, and you've got the ingredients for a cosmic cocktail recipe. Ethyl formate, in particular, thrives in the icy coatings of dust grains where simple molecules link up under the faint energy of starlight. Given enough time, millions of years, perhaps these molecules could hitch rides on comets, seeding young planets with the building blocks of flavor and maybe even life. Now, before you picture the galaxy as a giant fruit salad soaked in rum, there's a catch. Space is a vacuum, so those tantalizing scents aren't wafting anywhere. Even if you could stick your head into Sagittarius B2, the lack of air would mean no smell at all, just instant suffocation. Plus, ethyl formate shares the stage with less charming odors like ammonia and formaldehyde, turning the Milky Way's perfume into something closer to a ChemLab spill cabinet. Yet the sheer presence of these molecules is mind-bending. They prove that the raw materials for complex organic chemistry, and yes, even the essence of your favorite desserts and drinks, exist out there, woven into the fabric of the galaxy. It's a reminder that the universe isn't just sights and sounds, but scents too, waiting in the dark for someone or something to notice. So next time you catch the aroma of ripe berries or a fine spirit, think bigger. You're getting a whiff of the cosmos itself. Ever wonder what would happen if you could hover just above the edge of a black hole, watching time unravel around you? Thanks to Einstein, we know something mind-bending. Time itself slows down near these cosmic monsters, warping like taffy stretched to its limit. This isn't science fiction, it's gravitational time dilation, a real phenomenon where gravity's grip literally bends the fabric of space-time, turning minutes into years for anyone watching from afar. Think back to Interstellar, where Matthew McConaughey's character spends what feels like mere hours on a planet orbiting the black hole Gargantua, only to return to his ship and find his crewmate has aged decades. That wasn't just Hollywood exaggeration, it was physics in action. near a black hole's event horizon where gravity is so strong not even light can escape, time crawls to a near standstill. A single hour there could mean years passing elsewhere in the universe. For every tick of your clock inches from the abyss, Earth might see thousands of sunrises and sunsets without you. Why does this happen? Einstein's general relativity tells us that massive objects like black holes create deep wells in space-time. The steeper the well, the slower time flows at the bottom compared to the surface. Picture two clocks, one placed on Earth, the other near a black hole. The first ticks steadily, marking seconds as we know them. The second, each tick stretches longer and longer, like a metronome submerged in molasses. This isn't just theoretical. GPS satellites orbiting Earth have to account for microscopic time differences caused by our planet's gravity, or their navigation would drift by miles. Near a black hole, the effect isn't microscopic, it's catastrophic. Here's where it gets even wilder. If you could somehow skim the event horizon without being torn apart, you'd witness the universe's entire future unfold in fast forward. Stars would blaze and die like fireflies, galaxies would collide and merge, all while you hovered in what felt like moments. It's a one-way ticket to the distant future with no return. And the closer you get, the more extreme the distortion. Cross the event horizon and time, as we understand it, ceases to exist. Your final seconds from an outside perspective could span eternity. But don't pack your bags for time travel just yet. Black holes don't just bend time, they shred anything that ventures too close. The tidal forces would stretch you into a human noodle long before time dilation could offer any benefit. And while we've observed this effect indirectly, like with stars orbiting our galaxy's central black hole, no human will likely ever experience it firsthand. Yet the implications are staggering. Black holes aren't just cosmic vacuum cleaners, they're time machines forged by gravity, proving Einstein right in the most dramatic way possible. They show us that time isn't the rigid, universal constant we once thought. It's fluid, malleable, and utterly at the mercy of the universe's heaviest curbs. So next time you check your watch, remember, somewhere out there in the shadow of a black hole, time is moving at a whisper while yours races on. While most planets spin like graceful tops as they orbit the sun, Uranus tumbles through space like a drunken cosmic ball, rolling on its side with an outrageous 98-degree axial tilt. Imagine a spinning top knocked sideways, wobbling along its path. That's Uranus performing a barrel roll around the sun while the other planets twirl upright. This bizarre orientation means its poles take turns basking in decades of continuous sunlight or plunging into equally long winters, while its equator gets barely any seasonal change at all. Stack this against Earth's tidy 23.5-degree tilt and the difference is laughable. Our planet's gentle lean gives us predictable seasons, summer when our hemisphere tilts sunward, winter when it tilts away. But Uranus, its tilt is so extreme that for a quarter of its 84 Earth-year orbit, one pole points directly at the sun while the other drowns in darkness. Picture standing at the North Pole during its summer. The sun wouldn't rise or set. It'd just spiral lazily overhead like a slow-motion spotlight for 21 straight years. How did Uranus end up so lopsided? The leading theory involves a cataclysmic collision, a smash-up with an Earth-sized object early in the solar system's history that literally knocked the planet sideways. Some simulations suggest not just one impact, but a series of violent strikes that sent Uranus into its dizzying roll. Others argue gravitational tugs from Saturn and Jupiter may have gradually torqued its axis over eons. Whatever the cause, the result is a world where compasses would spin uselessly and navigation would be a nightmare. Even Uranus weather rebels against norms. While gas giants like Jupiter boast iconic striped storms, Uranus's atmosphere is oddly bland, just a pale blue-green haze with few visible features. But don't be fooled. Its winds scream at 560 miles per hour, and when Voyager 2 flew by in 1986, it caught glimpses of fleeting storms and a mysteriously weak magnetic field offset from the planet's center. This sideways world keeps defying expectations, proving that in our solar system, normal is just a suggestion. So next time you picture planets spinning politely around the sun, remember Uranus, the cosmic rebel that rolls to its own rhythm, turning the rules of orbital mechanics into a cosmic punchline. Among the swirling storms and golden bands of Saturn, there's a structure so precise it looks machined, a gargantuan hexagon spinning around the planet's north pole, its 6 razor-straight sides stretching wider than Earth itself. This isn't some trick of light or camera artifact. It's a real, persistent storm system, a hurricane with geometry so perfect it defies everything we know about planetary weather. When the Cassini probe first captured clear images of this phenomenon in 2006, scientists were stunned. Storms don't form hexagons, at least not naturally. Yet there it was, a cosmic honeycomb etched into Saturn's atmosphere, churning for decades, possibly centuries, without breaking its impossible shape. What makes this hexagon even stranger is its sheer scale. Each side spans nearly 9,000 miles, long enough to stretch from New York to Tokyo and back, with winds howling at over 200 miles per hour. The structure isn't flat like a stop sign. It's a towering 3-dimensional vortex plunging 60 miles deep into Saturn's atmosphere, its walls stacked with layers of churning gas. And unlike Earth's hurricanes, which fade in days or weeks, this hexagon has persisted since Voyager first glimpsed it in the 1980s, outlasting every storm in recorded human history. How does such a geometric freak exist? The leading theory points to Saturn's wild atmospheric dynamics. On a planet where jet streams race faster than bullets, the hexagon might be a standing wave, a kind of atmospheric resonance where winds shear against each other at just the right speeds to pinch the storm into shape. Picture water swirling around a drain, but on a planetary scale where the planet's rotation and internal heat create stable patterns in the chaos. Laboratory experiments with spinning fluids have recreated simpler polygons, suggesting the hexagon could be a natural, if rare, outcome of fluid dynamics in gas giants. But Saturn loves to complicate things. Unlike Jupiter's turbulent storms which flare and vanish, the hexagon remains eerily stable, anchored to the North Pole like a cosmic badge. Some researchers speculate deeper forces are at play, perhaps interactions between Saturn's magnetic field and its atmosphere, or hidden convection currents rising from deep within the planet. Others wonder if the hexagon is a visual echo of something deeper, like vibrations from Saturn's interior shaping its clouds the way sound waves mold patterns in sand. And then there's the color mystery. The hexagon wasn't just a shape, it was a chameleon. When Cassini arrived during Saturn's northern winter, the storm was a dusky blue cloaked in shadows. But as spring dawned in 2012, the hexagon morphed into a golden haze, its hue shifting with the seasons like some alien autumn. Scientists suspect sunlight reacting with atmospheric chemicals caused the change, but the exact recipe remains unknown. The hexagon isn't just a curiosity, it's a masterclass in planetary science. It forces us to question assumptions about fluid behavior, weather extremes, and how energy moves in alien atmospheres. While Earth storms rage and dissipate, Saturn's geometric tempest spins on, a monument to the universe's ability to craft order from chaos. So the next time someone calls nature untidy, point them to Saturn, where the skies boast a polygon so perfect it could have been drawn by the cosmos itself. The moon isn't the silent, lifeless orb it appears to be. It shakes, rattles, and rolls with its own version of earthquakes. These lunar tremors, fittingly called moonquakes, were first discovered when Apollo astronauts planted seismometers on the surface in the late 1960s and early 70s. What they recorded shattered expectations. Our cosmic companion is far more seismically active than anyone imagined. with vibrations ranging from faint whispers to ground-shaking jolts that would register as a 5 on the Richter scale. Unlike Earth's quakes, which stem from tectonic plates grinding against one another, moonquakes have stranger origins. Some are triggered by the same gravitational tug of war that gives Earth its tides. As our planet's gravity stretches and squeezes the moon, it creates deep tremors centered nearly 700 miles below the surface, far deeper than any earthquake could reach. Others are thermal quakes, the lunar equivalent of a frozen lake cracking on a winter night. When the moon's surface transitions from scorching 260-degree daylight to minus 280-degree darkness in hours, the sudden contraction causes the brittle crust to snap like an overstressed ice sheet. But the most unsettling moonquakes are the shallow ones, which can last up to 10 times longer than earthquakes. Without an atmosphere or water to dampen the vibrations, these tremors ripple across the moon like a struck gong, sometimes continuing for hours. Apollo seismometers picked up thousands of these events, including a particularly violent cluster near a region called the Mare Serenitatis. Scientists suspect these might be linked to ancient landslides or shifting debris in long-cooled lava tubes, remnants of the moon's volcanic past. Here's what's truly bizarre: some moonquakes are man-made. When the Apollo lunar modules deliberately crashed back onto the surface after delivering astronauts home, the impact sent seismic waves racing through the moon, giving scientists their first look at its internal structure. Those echoes revealed a surprising fact: the moon might still have a partially molten core, a sliver of its fiery youth lingering beneath the dust. So while the moon lacks the constant tectonic drama of Earth, it's far from dead. Its quakes paint a picture of a world still settling, still feeling the pull of its parent planet, still cracking under the strain of extreme temperatures. Those silent tremors remind us that even in the stillness of space, nothing is ever truly at rest. Humanity has flung its calling cards into the cosmic ocean. Voyager 1 and 2, our most distant messengers, have sailed beyond the reach of our sun's influence and into the interstellar void. Launched in 1977, these twin probes weren't designed to leave the solar system, yet they've outlived their original missions by decades, becoming the first human-made objects to breach the invisible boundary where the solar wind yields to the milk of the galaxy itself. Voyager 1 punched through first in 2012, crossing the heliopause, the turbulent region where particles streaming from the sun collide with those from distant stars. Its sibling, Voyager 2, followed in 2018, confirming that the first breakthrough wasn't a fluke. Both probes now drift in true interstellar space, where the weather comes not from our sun, but from ancient supernovas and the magnetic fields of neighboring stars. They're still phoning home, their faint signals taking over 20 hours to reach Earth, each transmission weaker than a refrigerator light bulb. What's mind-blowing isn't just their distance, over 15 billion miles away and counting, but what they carry. Each Voyager holds a golden record, a 12-inch gold-plated copper disc packed with sounds and images meant to tell Earth's story to any extraterrestrial finders. There's Bach concertos, Navajo chants, the crackle of thunderstorms, even the brainwaves of a woman in love, all etched into grooves playable with the included stylus. The covers bear pulsar maps pointing back to our solar system and symbolic instructions for playback, a cosmic message in a bottle tossed into the galactic tides. Their paths tell a tale of celestial billiards. Voyager 1 used Saturn's gravity to slingshot northward, escaping the solar system's flat plane, while Voyager 2 danced past Jupiter, Saturn, Uranus, and Neptune, threading the needle between their moons like a spaceship in an arcade game. Now their trajectories diverge forever. Voyager 1 angles toward the constellation Ophiuchus, while Voyager 2 speeds toward Sirius. In 40,000 years, they'll drift within a few light-years of other stars, silent, perhaps dormant, but carrying whispers of a species that once dared to reach beyond its cradle. Yet even now, their aging instruments sniff the interstellar medium, detecting the faint hum of plasma waves and cosmic rays, data rewriting textbooks about the space between stars. Their plutonium power supplies dwindle by the year, likely going dark by 2030, but their mission isn't over until the last transmitter falls silent. Until then, these time capsules from the analog age continue their lonely odyssey, two sparks of human curiosity adrift in the endless dark. Every glowing star, every swirling galaxy, every planet you've ever seen, it's all just the tip of the cosmic iceberg. What we perceive as the universe, the glittering tapestry of light and matter, accounts for less than 5% of everything that exists, the rest. An invisible empire of dark matter and dark energy, two shadowy forces that puppet the cosmos in ways we're still struggling to understand. Let's start with dark matter, the universe's hidden scaffolding. In the 1930s, astronomer Fritz Zwicky noticed something odd about galaxy clusters. Their visible mass couldn't possibly generate enough gravity to hold them together. They should have flown apart like sparks from a firework. Later, Vera Rubin's studies of spinning galaxies revealed stars orbiting just as fast at the edges as near the centers, breaking Newton's laws, unless some unseen mass was anchoring them. That missing mass, dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, yet outweighs normal matter 5 to 1. Picture a snow globe where the water is dark matter, and the glitter is every star and planet we can see. Then there's dark energy, the universe's rebellious force. In the late 1990s, measurements of distant supernova showed the cosmos wasn't just expanding, it was accelerating. Something was fighting gravity's pull, stretching space-time faster and faster. That something, dubbed dark energy, comprises about 70% of the universe's total content. Unlike dark matter, which clumps and gathers, dark energy seems woven into the fabric of space itself, growing stronger as the universe expands. The numbers stagger. If the universe were a pie chart, a sliver, just 5% would be stars, planets, and gas. 25% would be dark matter and 70% dark energy. We're living in the crumbs of a much vaster reality, blind to most of what surrounds us, yet we know these phantoms exist by their fingerprints. Dark matter's gravity bends light around galaxies like cosmic lenses, creating rippled mirages of distant objects. Dark energy leaves its mark in the way galaxy clusters spread apart over billions of years. Even now, experiments deep underground hunt for dark matter particles, while telescopes map dark energy's push on the large-scale structure of the universe. Here's the humbling truth: for all our telescopes and equations, we're like goldfish in a bowl, unaware the water exists until someone taps the glass. The universe isn't just stranger than we imagine. It's stranger than we can imagine, with 95% of its story still written in invisible ink. The universe isn't just a silent movie, it's a symphony, with stars belting out vibrations that scientists have translated into eerie, haunting melodies. Through a process called astrosismology, astronomers listen to the pulses and quakes rippling through stars, converting their rhythmic flickers into sound waves we can actually hear. Our own sun, that familiar yellow disk in the sky, hums a deep, resonant note, a B-flat 57 octaves below middle C, so low it's beyond human hearing, but when sped up, it becomes an unearthly chorus of crackles, booms, and distant-sounding moans. These stellar songs aren't random noise, they're the fingerprints of a star's internal structure. Just as earthquakes reveal secrets about Earth's core, starquakes, or rather, star pulses, unravel what's happening beneath a star's blazing surface. When gas churns in a star's interior, it creates pressure waves that travel outward, making the entire star vibrate like a ringing bell. Telescopes like NASA Kepler and ESA's Gaia detect these subtle brightness changes, sometimes as small as 1 part in a million, painting a picture of the star's density, composition, and even age. The sun's song is particularly mesmerizing. Layers of superheated plasma inside it vibrate at different frequencies, creating overlapping tones that, when translated, sound like something between whale calls and a hum from a sci-fi spaceship. The harmonics are so precise that scientists can actually detect missing notes, frequencies that shouldn't exist if the sun were purely gas, hinting at hidden complexities in solar physics. Some stars, like red giants, produce deeper, slower rumbles, while younger, hotter stars emit rapid, high-pitched pulses, each one a unique voice in the galaxy's choir. But the real magic happens when these sounds are compressed into a range our ears can process. The result, a celestial concert where massive, churning balls of plasma become singing entities. One particularly famous recording, captured by the Solar and Heliospheric Observatory SOHO, transforms the sun's vibrations into a ghostly drone that seems almost alive. Other stars, like KIC 76723881, a distant sun observed by Kepler, reveal chaotic, jazz-like improvisations, their frequencies shifting unpredictably as magnetic fields twist and tangle inside them. These cosmic melodies aren't just beautiful, they're revolutionary. By listening to stars, scientists have uncovered rogue planets, detected hidden companion stars, and even predicted stellar explosions before they happen. The universe isn't just something we see, it's something we can hear, if only we know how to translate its vibrations. So next time you step outside and feel the sun's warmth, remember, it's not just shining. It's singing, and somewhere out there, in the depths of space, countless other stars are joining the chorus. If you think Earth's blazing orange sunsets are spectacular, wait until you see Mars's version, a surreal, cooling blue glow that looks like something out of a sci-fi dream. While our skies turn fiery at dusk thanks to Rayleigh scattering, where sunlight bounces off nitrogen and oxygen molecules, filtering out blue light and leaving reds and oranges, Mars flips the script entirely. There, the sunset isn't a warm farewell but an eerie azure whisper, courtesy of an atmosphere that's the polar opposite of ours. The magic lies in the Martian air, or rather, the lack of it. Earth's thick atmosphere scatters shorter blue wavelengths of light throughout the day, which is why our sky appears blue. But when the sun dips low, its light passes through more atmosphere, scattering the remaining blue away and leaving the longer, redder wavelengths to paint the horizon. Mars, with its paper-thin atmosphere just 1% as dense as Earth's, does the reverse. Fine dust particles suspended in its air are perfectly sized to scatter blue light when the sun's rays slant through at sunset, casting the sky in a soft cobalt hue. Red light, instead of dominating, slips straight through, barely touched, giving the sun itself a pale, diminished appearance. This isn't just theory, we've seen it firsthand. NASA rovers, from Spirit and Opportunity to Curiosity and Perseverance, have captured time lapses of these otherworldly sunsets. Side by side, the difference is staggering. Earth's sunsets explode with warmth, while Mars's fade into a tranquil, almost melancholic blue. The dust responsible for this spectacle isn't just any dirt. It's iron-rich regolith pulverized into particles about 1 micron wide, the ideal size to play with light in this unexpected way. But here's the twist: Mars's sky isn't blue all day. At high noon, when sunlight takes a shorter path through the atmosphere, the dust scatters red light more effectively, bathing the landscape in a familiar butterscotch glow. It's only when the sun grazes the horizon that the blue effect takes over, a fleeting daily metamorphosis. And because Martian dust storms can swell to engulf the entire planet, the intensity of these sunsets shifts with the seasons. More dust means more dramatic blues, while clearer skies soften the effect. This isn't just a pretty cosmic quirk, it's a clue to Mars's past. The prevalence of fine dust suggests eons of erosion, likely from ancient water and wind, grinding rocks into the perfect sunset makers. And while future colonists might miss Earth's fiery evenings, they'll trade them for something equally poetic: standing on rust-colored plains, watching a blue sun dip below the horizon, its light filtered through the dust of a world that was once far more like our own. Pluto's journey around the Sun isn't just a leisurely stroll, it's a glacial marathon, a single orbit stretching 248 Earth years. To put that in perspective, the last time Pluto completed a full year, the United States hadn't even declared independence, Mozart was a toddler, and the Industrial Revolution was still a distant dream. This dwarf planet moves so slowly that since its discovery in 1930, it's traveled less than a third of its way around the Sun. If you were born on Pluto, somehow surviving the negative 400-degree temperatures, you'd still be waiting for your first birthday party by the time your great-great-great-great-grandchildren celebrated theirs back on Earth. The sheer scale of Pluto's year becomes even more staggering when you consider how much human history fits into just one of its orbits. When Pluto last reached its current position in the solar system, the world looked unrecognizable, no electric lights, no airplanes, no photographs. The next time it returns to this spot, in the year 2178, who knows what technologies or civilizations might exist? Entire empires could rise and fall in the time it takes this tiny world to circle the Sun once. NASA's New Horizons mission gave us our first close-up glimpse of Pluto in 2015, revealing a shockingly vibrant world. The images showed heart-shaped glaciers of nitrogen ice, towering water ice mountains, and skies tinged blue by hydrocarbon haze. But here's the kicker. By the time Pluto completes just 1% of its orbit, about 2.5 Earth years, New Horizons will be ancient history. The spacecraft, now venturing deeper into the Kuiper belt, will have long since gone silent, its plutonium power source exhausted. Future missions launched centuries from now might arrive to find Pluto's surface utterly transformed, ices shifted, atmospheres thickened or vanished because even minor seasonal changes there unfold over decades. Pluto's sluggish pace creates bizarre cosmic poetry. Its elliptical orbit sometimes brings it closer to the Sun than Neptune, as it did from 1979 to 1999. During those brief decades of relative warmth, Pluto's thin atmosphere expanded, allowing nitrogen and methane gases to escape into space like a slow-motion balloon deflating. Now, as it retreats back into the deep freeze, those gases are snowing back onto its surface, painting fresh layers of frost across its rugged terrain. What does time even mean on such a world? A single Pluto day lasts 6.5 Earth days, meaning a newborn there would experience over 14,000 sunrises before their first birthday. Seasons don't so much change as ooze forward, with decades-long springs giving way to equally drawn-out summers. The very concept of a year becomes almost meaningless when it spans generations. Yet this extreme timescale offers a humbling reminder. Our lives, our civilizations, even our species' entire history are but brief flickers against the cosmic clock. Pluto doesn't care about our calendars or deadlines. It moves to rhythms written in gravitational ink, dancing to a tune only the universe can hear. So next time you feel rushed, think of Pluto, where time isn't measured in minutes, but in the slow, patient turning of the galaxy itself. On a planet named HD 189733b, the skies don't just weep rain. They unleash a horizontal storm of molten glass. This cobalt-blue world, orbiting dangerously close to its star, is a masterpiece of cosmic violence. Winds howl at 5,400 miles per hour, 7 times the speed of sound, carrying with them not water droplets, but shards of glass sharp enough to flay flesh. If you could somehow stand on its surface, and you absolutely couldn't, you'd be sliced apart by a sandblaster of superheated silica before you even had time to scream. Scientists first spotted this monstrosity in 2005, using the Doppler wobble method, detecting subtle tugs on its star as the planet orbits. But the real horror show unfolded when astronomers trained the Hubble Space Telescope on it, analyzing starlight filtering through its atmosphere. the spectrum revealed something chilling, the telltale signature of silicate particles, the building blocks of glass suspended in its stratosphere. Combined with temperature readings soaring above 1,800 degrees Fahrenheit, the conclusion was unavoidable. This isn't just a hot Jupiter. It's a celestial grinder where entire clouds vaporize, condense, and fall as razor-edged rain sideways. Artist renditions paint a nightmare straight from Dante's Inferno. The planet's deep blue hue, caused by light scattering off silicate haze, gives it the deceptive calm of an earthly ocean. But zoom in and the illusion shatters. Storms rip across its surface like cosmic sandpaper, dragging streams of molten glass through an atmosphere thick with vaporized metals. Day and night don't exist here. The planet is tidally locked, one side forever scorched by its star, the other locked in endless howling twilight. How do we know all this from light years away? The magic lies in transit spectroscopy. When HD 189733b passes in front of its star, certain wavelengths of starlight get absorbed by its atmosphere, leaving dark lines in the spectrum like a barcode. Decode those lines and you've got a chemical inventory of alien skies. In this case, the data screamed silica, not as tranquil beach sand, but as a tempest of tiny daggers. Yet even this hellscape holds clues to planetary diversity. Its extreme weather forces us to rethink how atmospheres behave under brutal stellar radiation. Some theorize the glass rain might eventually coat the planet's surface in a brittle, translucent crust, a frozen record of its own brutality. Others wonder if similar processes happen on cooler worlds where the glass might be something even stranger. So while HD 189733b will never be a vacation destination, it's a laboratory for the impossible, a reminder that the universe's creativity for horror rivals its capacity for beauty. Out there, beyond the safety of our Goldilocks zone, the skies don't follow rules, they rewrite them. Those crisp, pitch-black shadows you see in Apollo mission photos aren't a camera trick or Photoshop effect, they're the moon's brutal reality. Without an atmosphere to scatter sunlight, shadows on the lunar surface don't fade into gentle gradients like Earth's. They're razor-sharp abysses of pure darkness, as if someone flipped a switch between light and void. When Neil Armstrong took his first steps, his boot left a footprint so starkly defined it looked like it had been stamped into wet concrete, while the shadow cast by the lunar module could have been cut out with a knife. Earth's shadows soften thanks to our atmosphere's magic trick. Air molecules bounce sunlight in every direction, filling in the dark edges with scattered rays. It's why your shadow on a sunny day has a faint halo of light around it, but on the moon, one step into the shade means plunging into absolute blackness even at high noon. Astronauts reported struggling with depth perception near crater rims or boulders, where the sudden drop into shadow erased all detail. Some couldn't even see their own feet if they stood in darkness despite the sun blazing overhead, a disorienting effect no earthly experience prepares you for. The contrast is so extreme it messed with technology too. Apollo cameras designed for Earth's softer lighting often overexposed sunlit areas while leaving shadows as inky blotches. In one famous photo of Buzz Aldrin, his visor reflects the lunar module, but his face, tucked in shadow beneath his helmet's rim, is completely invisible. Back home, even the deepest canyon at midday gets a whisper of indirect light. On the moon, walk behind a rock and you're in a darkness so complete it feels like stepping off the edge of the universe. This isn't just a quirk, it's a lethal hazard. NASA trained astronauts using simulated lunar lighting in abandoned aircraft hangars, dangling black curtains to mimic the void like shadows. They quickly learned that without Earth's atmospheric cushion, there's no twilight zone, just a binary choice between blinding glare and abyssal night. Future moon settlers will need navigational aids to avoid stumbling into craters hidden by these optical traps, where one wrong step could mean vanishing into the dark. Yet those shadows also preserve history. with no wind or rain to erase them. Footprints and rover tracks from 50 years ago still carve crisp outlines into the dust, their shadows as sharp as the day they were made. They're frozen moments in time, a reminder that on the moon, even darkness has permanence. So next time you see a crescent moon hanging in the sky, picture those knife-edge shadows where sunlight ends, the universe doesn't fade. It stops. When galaxies collide, it's nothing like the fiery crashes you see in movies. Picture this: the Andromeda Galaxy, a swirling behemoth of 1 trillion stars, is hurtling toward our Milky Way at 250,000 miles per hour. In about 4 billion years, these two cosmic titans will meet, yet despite the apocalyptic imagery that might conjure, not a single star is likely to smash into another. Why? Because space is so unbelievably empty that even in a head-on galactic merger, stars slide past each other like ghosts in the night. Think of it this way: if the Sun were the size of a grapefruit in New York City, the next nearest star, Proxima Centauri, would be another grapefruit all the way in Los Angeles. Now scale that up to a galaxy with hundreds of billions of stars, each just as isolated. When Andromeda and the Milky Way intertwine, their stars will be like handfuls of sand tossed into a swimming pool most grains never touch. The real drama happens on an entirely different scale: gravitational chaos. As the galaxies merge, their colossal gravitational pull will warp and stretch both structures beyond recognition. Spiral arms will shred into streamers of stars, and immense tidal forces will fling some stars clear into intergalactic space. Computer simulations show a mesmerizing dance. First, a near miss that bends both galaxies into weird, elongated shapes, then multiple passes over hundreds of millions of years before they finally settle into a single, bloated elliptical galaxy. During this slow-motion crash, gas clouds, the only components dense enough to actually collide, will slam together, triggering bursts of new star formation so intense they'll outshine entire galaxies. Yet through all this upheaval, star systems like ours will likely remain unscathed. Even as the Milky Way's familiar spiral disintegrates, our solar system will probably just get tossed into a new orbit farther from the galactic core. The night sky, though, will transform beyond recognition. Andromeda, now a faint smudge, will dominate the heavens as it grows larger and closer, first as a distorted streak, then as a fragmented disk, until finally the two galaxies blend into one. Here's the wildest part: this isn't some rare cosmic catastrophe. Galactic collisions are commonplace. The Hubble Space Telescope has captured dozens of mergers in progress, galaxies twisted into rings, tails, and even mice-shaped pairs with long streams of stars trailing behind. Some, like the antennae galaxies, are caught mid-collision, blazing with newborn stars from colliding gas clouds. Others, like NGC 7252, show the aftermath, a serene elliptical galaxy with no trace of its violent past except the orbits of its stars. So while the phrase galactic collision sounds like destruction on an unimaginable scale, the truth is subtler and far more beautiful. It's less a crash than a rearrangement, a gravitational tango where stars weave past each other in an intricate billion-year ballet. The universe doesn't do smash-ups, it does mergers, quiet, inevitable, and breathtakingly slow. Every second, the Sun sheds 4 million tons of its mass, not as chunks drifting into space, but as pure energy radiating outward in a process so efficient it powers all life on Earth. That staggering loss happens through nuclear fusion, the same reaction we've tried and failed to replicate in labs here on Earth. Deep in the Sun's core, under pressures 250 billion times stronger than our atmosphere, hydrogen atoms slam together to form helium. But here's the catch: the resulting helium weighs slightly less than the original hydrogen. That missing mass, it's converted into energy via Einstein's famous E=mc², where even a tiny bit of mass produces an unimaginable amount of energy. To put this into perspective, let's scale it down. 4 million tons per second sounds abstract until you realize it's equivalent to the weight of 15,000 fully loaded Saturn V rockets, the kind that launched Apollo missions vaporized into pure energy every single tick of the clock. Yet despite this colossal loss, the Sun is so massive that over its entire 10 billion-year lifespan, it'll shed just a fraction of a percent of its total weight. It's like a billionaire spending $1,000 a second after a century. They'd still be impossibly rich. Now compare that to humanity's energy appetite. All the electricity, fuel, and power consumed by every person on Earth in a year amounts to roughly 600 exajoules. The Sun, it produces that same amount in milliseconds. In the time it takes you to snap your fingers, our star generates enough energy to power human civilization for 500,000 years. The numbers are so vast they border on absurdity, proof that nature's fusion reactor operates on a scale our minds aren't wired to grasp. But here's what's wild: we're inside this energy flow. Every photon that warms your skin, every sunbeam that fuels photosynthesis, is a tiny fragment of that 4 million ton per second sacrifice. The Sun isn't just hanging in the sky. It's actively dissolving, its substance transformed into the light that shapes our world. And because these photons take 100,000 years to escape the Sun's dense interior, the warmth you feel today was generated back when early humans were first discovering fire. Yet for all we take from the Sun, we give almost nothing back. Our entire planet intercepts just 1/2 billionth of its total output, a rounding error in the cosmic ledger. Even if we could capture every drop of sunlight hitting Earth, it wouldn't make a dent in the Sun's budget. This isn't just a lesson in astrophysics, it's a humbling reminder of our place in the universe. We orbit a furnace so generous, so unfathomably vast, that it can lose mountains per second without flinching, and still have enough fuel to burn for billions of years to come. The solar system isn't just floating in empty space, it's encased in a vast, invisible bubble created by the Sun's own breath. This cosmic fortress, known as the heliosphere, stretches far beyond Pluto, shielding us from the harsh interstellar winds like a spaceship's force field. And right at its edge, where the Sun's influence finally surrenders to the galaxy, Voyager 1 stumbled upon something extraordinary: a wall of hydrogen, a swirling barrier of ancient atoms marking the boundary between our celestial neighborhood and the great unknown. This hydrogen wall isn't some solid structure, it's more like a cosmic shoreline where two oceans meet. On one side, the solar wind, a supersonic stream of charged particles from the Sun, pushes outward, carving out a protective cavity in space. On the other, the interstellar medium, a thin soup of gas and dust left over from ancient supernovas, presses back. Where these forces collide, hydrogen atoms pile up like leaves caught in a gutter, slowed and heated by the clash. Voyager's sensors detected this buildup as a sudden spike in ultraviolet light, the telltale glow of hydrogen atoms getting slammed by incoming stellar radiation. What makes this wall so fascinating is how it reshapes our map of the solar system. For decades, scientists pictured the heliosphere as a sleek, comet-shaped bubble, with the Sun's motion through space creating a nose and a trailing tail. But Voyager's data revealed a messier truth: the boundary ripples and folds, more like a crumpled blanket than a smooth surface. The hydrogen wall acts as a buffer zone, absorbing some of the interstellar wind's punch before it reaches the inner solar system. Without it, Earth might be bathed in far more cosmic rays, those high-energy particles that pose risks to both astronauts and electronics. Here's the twist: this wall isn't unique to us. Every star blowing a stellar wind likely has its own version, a fingerprint of its interaction with the galaxy. Some, like red giants, might have heliospheres thousands of times larger than ours, while tiny, dim stars could have bubbles so small they barely shield their planets. The hydrogen wall is just one piece of a much larger puzzle: how stars carve out safe havens in the chaotic interstellar sea. Yet for all its importance, this barrier is ghostly thin. The density of hydrogen here is still millions of times lower than Earth's atmosphere, so crossing it wouldn't feel like breaking through anything tangible. Voyager slid past without a shudder, its instruments registering only subtle shifts in particle energy and magnetic fields. But symbolically, that wall is the last outpost of home, the point where the sun's voice fades to a whisper and the galaxy's chorus takes over. So the next time you bask in sunlight, remember, it's not just warmth on your skin. It's the end point of an epic journey, a river of particles that raced to the edge of the solar system, fought its way through a hydrogen barrier, and now, billions of miles later, gently lands on your face, a cosmic message in a bottle sent from the heart of our star. Earth doesn't just have one moon, it has a secret entourage of tiny, temporary companions you've never heard of. These mini-moons are asteroids, usually no bigger than a washing machine, that get snatched by Earth's gravity and whipped into chaotic orbits around us for months or even years before cosmic chance flings them back into space. One of the most famous, a car-sized rock called 2020 CD3, circled Earth for nearly 3 years before we even noticed it, a cosmic stowaway hiding in plain sight. What makes these mini-moons so elusive? Unlike our familiar lunar companion, which follows a predictable, near-circular path, these captured asteroids tumble along wild, stretched-out orbits that resemble tangled spaghetti. Some loop around Earth in a chaotic dance, influenced by both our planet's gravity and the sun's relentless pull. Others hover at gravitational waypoints called Lagrange points, where competing forces create pockets of stability. For example, 2020 CD3 traveled a wobbly, horseshoe-shaped path that took it twice as far as the Moon before swinging back toward us, an orbital oddity that made it nearly invisible to telescopes until it was practically in our backyard. Detecting these cosmic hitchhikers is like trying to spot a speeding motorcycle with its headlights off at midnight during a rainstorm. They're faint, fast-moving, and often camouflaged against the starry backdrop. Most are discovered purely by accident, their presence betrayed only by streaks in long-exposure telescope images. Even then, confirming their orbits requires painstaking calculations to untangle whether they're genuine mini-moons or just regular asteroids making a close pass. The Pan-STARRS telescope in Hawaii, which found 2020 CD3, scans the same patch of sky repeatedly to catch these subtle intruders. But for every one we spot, scientists estimate dozens more slip by unnoticed. Why does Earth even have these temporary moons? Blame gravitational opportunism. When small asteroids drift near Earth, our planet's gravity can momentarily catch them if their speed and angle are just right. It's like tossing a ball into a swirling eddy. Sometimes the currents trap it briefly before flinging it back out. These captures happen more often than you'd think. Simulations suggest at least one mini-moon is orbiting Earth at any given time, though most are too small or too distant to detect with current technology. The implications are thrilling. Mini-moons could one day serve as practice targets for asteroid deflection missions or even mining operations. Their weak gravity and close proximity make them ideal testing grounds for space missions without the fuel costs of traveling to the asteroid belt. Some scientists even speculate they might carry water ice or organic compounds, relics from the solar system's infancy preserved in their rocky bodies. Yet their transient nature adds a layer of poetry to their existence. These aren't permanent fixtures like our moon, they're fleeting guests, celestial mayflies that linger just long enough to remind us how dynamic our corner of space truly is. So the next time you gaze at the moon, remember, it might not be the only one keeping Earth company tonight. Somewhere up there, a tiny, unnoticed companion could be tracing its silent, looping farewell. Towering over the rusty plains of Mars like a sleeping titan, Olympus Mons doesn't just break records, it shatters them. This behemoth of a volcano stands nearly 16 miles tall, making Mount Everest's 5.5-mile summit look like a modest hill. Stack 3 Everests on top of each other, and you'd still need to add another Empire State Building just to reach Olympus Mons' peak. But height isn't its only staggering feature. This Martian monster is also wider than the entire state of Arizona, with a base spanning 370 miles. If you could teleport it to Earth and plop it down over Paris, its edges would stretch all the way to London, Amsterdam, and Munich, swallowing Western Europe in a single geological yawn. What makes Olympus Mons so preposterously large? The answer lies in Mars's lack of tectonic drama. On Earth, shifting continental plates spread volcanic activity across multiple sites, preventing any single volcano from growing too dominant. But Mars is a one-plate planet. Its crust remains static, allowing lava to pile up in the same spot for billions of years without interruption. Picture a tube of toothpaste squeezed endlessly in one place. Olympus Mons is the result, a shield volcano built from thousands of overlapping lava flows, each adding another layer to its gently sloping bulk. Its summit caldera alone could swallow 50 cities, a gaping maw large enough to fit entire mountain ranges inside. The scale becomes surreal when you map it onto Earth. Imagine standing in San Francisco and seeing a mountain so wide it blocked the horizon from Seattle to San Diego. Its upper slopes would pierce the stratosphere, poking into regions where jetliners dare not fly. Yet despite its size, climbing Olympus Mons would feel deceptively easy. Its average incline is a mere 5 degrees, a gentle ramp by mountain standards. You wouldn't need ropes or ice axes. You'd need a reliable rover and enough oxygen to last weeks. But here's the twist: Olympus Mons might still be alive. While its last eruption likely occurred tens of millions of years ago, Mars lacks the erosional forces that quickly weather Earth's volcanoes. Without rain, wind, or tectonic recycling to wear it down, Olympus Mons remains eerily pristine, its lava channels and cliffs looking freshly formed. Some scientists speculate that magma could still lurk deep beneath its base, waiting for the planet's next geological wake-up call. This isn't just a mountain, it's a monument to planetary differences, a testament to what happens when a world's geology leans into a single idea for eons. While Earth spreads its fire across hundreds of volcanoes, Mars went all in, crafting a colossus that dwarfs anything in our solar system. So next time you gaze at Earth's peaks, remember, they're just foothills compared to the king next door. From drifting moons raining glass to diamond planets and silent, screaming stars, the universe never runs out of ways to leave us breathless. Who could forget the hexagon storm wider than Earth, stubbornly spinning on Saturn for centuries, or the neutron star where a single teaspoon weighs more than a mountain? And let's not overlook the cosmic cocktail of raspberry-scented gas clouds, or the fact that 95% of the universe is invisible dark matter and dark energy pulling strings we can't even see. These aren't just facts, they're humbling reminders that reality outshines even our wildest sci-fi dreams. But here's the real magic: this is just the tip of the cosmic iceberg. Every discovery peels back another layer, revealing deeper mysteries waiting to be unraveled. Which fact blew your mind the most? Was it the backward spinning Venus, the moon's silent earthquakes, or the black hole humming a note 57 octaves below middle C? Drop your favorite in the comments. I'd love to hear which cosmic wonder made you pause and stare at the sky a little differently. And if you're hungry for more mind-bending journeys through space's greatest enigmas, don't forget to hit subscribe. The universe is vast and we've barely scratched the surface. As Carl Sagan once said, somewhere, something incredible is waiting to be known. So keep looking up, stay curious, and remember, the cosmos isn't just stranger than we imagine, it's stranger than we can imagine. Until next time, keep